we have a lot of things we can talk about, and we'll just see what questions we'll get stuck at and like want to go into more detail. And the very first question is just for Corey. I don't know if he's still around. Yeah, cool. So it looks like passing more goal states increases the amount of drunken wiggling in the robotic arm. Do you have any ideas on how to reduce that effect?
I'm not sure. No. Yeah, I don't know if...
It's okay. Yeah. Do you want to come on the stage?
Yeah, drunken wiggling. I think like a lot of what looks like drunken wiggling might just be kind of an artifact of the particular environment we're in. Like especially if you tried to extend this to a real system, I don't think that that sort of kind of high frequency motion would even be possible with like a realistic IK controller. And it's not clear to me that this kind of like high frequency motion is something that is kind of tied in a particular way to the goal condition versus the BC. So.
One minor comment on this is I have seen drunken wiggling out of robotic controllers before, so it is possible in the real world, certainly, at least from some of the baselines that I've evaluated in the past, but yeah.
Does it happen with behavioral cloning?
It wasn't a well, not that I know of, but I don't know.
I was thinking compound errors.
So there were a couple of questions on the important topic of how do we actually want to define task-agnostic reinforcement learning. So for example, what is the difference between multitask and task-agnostic reinforcement learning?
So I guess that task-agnostic reinforcement learning is a term that was invented just for the workshop. So I'm not sure it's possible to say a general thing, but my perspective, from what I understand, is that actually a number of interesting problems we discussed today are problems where there are no external rewards at all. So no external tasks at all. So that's a key difference with the multitask RL is that in multitask RL you have many tasks that are imposed by the experimenter. But then, as we saw in other talks, one efficient approach to do task-agnostic RL is actually to have internally many tasks, whether you call them auxiliary tasks or goals or whatever, and then it enables to do efficient task-agnostic RL. That's one perspective.
And I think we've seen an example of that, of this spectrum with Martin's talk in the morning. And so perhaps an interesting follow-up question here would be, where do we want to draw the boundary between rewards imposed by an engineer or an external reward compared to something that I can call an internal prior to the agent that is still some kind of task?
One thing I will comment on this difference, and I don't necessarily like to think too much about terminology. I don't think we necessarily need to put names to every single exact thing, but one kind of two distinct paradigms that I see, at least in the reinforcement learning community, is one where you have some set of reward functions that you're optimizing over, whether the reward functions come from a human or whether they come from your algorithm. And also the setting where kind of separately is where you know that in the future you will be given a reward function and you want to act in such a way that you know you'll be able to optimize that reward function in the future without having knowledge of what that reward function is right now. And I view in many ways task-agnostic RL as potentially as both of these types of paradigms, but the latter paradigm enables you to kind of, without knowing what the task is ahead of time, be able to prepare for that.
I'm trying to come up with a way to formulate how I'm thinking about these, but to me these are very related, whether we expose an external reward structure or something that we call internal. In the end, those are all design choices in how we set up the learning task for an agent. And to me, I don't really see a very fundamental difference there. I see the kind of research goal of trying to come up with reward structures that are more general than something that can learn for one very specific target task. So in the sense of how Chelsea described trying to pre-train for something where we don't know what the precise task is going to be at test time. But I'm not sure I see any more fundamental differences than that.
I would still, I mean, I understand what you say, but so first of all, from the point of view of an external user of a system, if there is one, there can be either sometimes some objective which are about solving a task associated with a reward, but sometimes objective is not about that, it's about learning a model of the world that can be used to for many things, but that's not like a task defined in terms of maximizing a reward, and so it's not completely equivalent. And then there is also the perspective, which I know many of you are not familiar with, but this is my perspective, which is about like when we want to try to model autonomous learning in the way it happens in animals, then there are just no external rewards. It just doesn't exist. And so in that perspective, there is a fundamental difference. There is not an engineer who has a task in the head that he wants the system to learn, and then those internal or auxiliary tasks are a tool to solve that. But the perspective is very different, and the way of evaluating is very different. So,
yeah, I might just add that even external rewards have to be understood internally as rewards, and that's not necessarily very easy to do. So you have to have quite a mature model of the world to even understand that you've succeeded in something. So yeah, a little bit of a false dichotomy maybe.
Okay, let's go on to the next question. Is TARL like language models, which are trained in task-agnostic settings? Should we expect a similar task-agnostic revolution in reinforcement learning?
So I'm thinking about shared structure that we can use across tasks, maybe in terms of some kind of pre-training. I haven't thought it so much in terms of language models, but what we've seen in computer vision. So in computer vision, the pattern that emerged is that a lot of very powerful vision models, for example, trained on ImageNet, were kind of ended up being very general purpose feature extractors that a lot of people started to build up on. And in reinforcement learning, I haven't quite seen a similar kind of development. I'm really curious whether TARL could play a similar role, but I'm not necessarily sure we have the right way to do this pre-training yet.
I think that I guess it is an interesting analog here in that language models in many ways encapsulate many different tasks in the NLP community, and is also can be viewed as a kind of form of unsupervised learning in some regard, and kind of related to also to the last two questions on this slide. I think that like things like language models can play a large role in this because if you basically learn a model of the world through unsupervised learning, then that is a very effective means for being able to transfer to many downstream tasks, even in such situations where you don't know what that downstream task is. And it's also kind of, at that last question, it's worth mentioning that you can also do the same sort of thing in a model-free way. And I actually presented some work in a different workshop this morning on one approach where you can do it in a model-free way, where we basically construct our own tasks and try to perform meta-learning across those tasks such that when we see a new task down the line, we can very quickly solve it through reinforcement learning. And so I think that this isn't just model-based RL. There are other approaches that we can take in order to prepare ourselves for downstream tasks, and that includes things like what I just mentioned, as well as things like intrinsic motivation, exploration, etc.
I mean, I think that having a task distribution, if I've understood what that means correctly, would actually be very helpful for psychology, where we've been studying tasks all as kind of atomic different things, like memory tasks and learning tasks, but we don't have any theory of how similar they are and how people generalize between them, and I think that might be hurting us in getting towards a more of a general understanding of intelligence. So I kind of welcome this, what we're seeing with things like OpenAI Gym and this kind of increasing taxonomy of tasks that are somewhat similar to one another, and I think that would help us understand human intelligence better as well.
Could maybe the limiting factor here be the environments and benchmarks that we have available? So I know OpenAI at some point had this universe kind of extension of GYM where it seems to have gotten a little bit quiet around that. And I think the long-term goal of that was to come up with so many tasks that you would, in essence, have a very dense sampling of tasks that might allow an agent to explore maybe in a task-agnostic way and then use that as a prior for something new. But maybe it's just we're not yet at the stage where we have that kind of very powerful world environment where we could get that kind of data.
Maybe to add also another dimension, and related to also an issue raised by Dana Prekop this morning about evaluation. So I think what is key is to understand the structure of the environment and of the task in which we put the agents we put in the sense that it's one thing to evaluate those systems by having single numbers in terms of a performance. It's another thing to understand more deeply, if I can say, what they are actually learning as policies, what is the strategy. And for doing this, it really requires to have an understanding of that environment. So for example, a benchmark task that is used in reinforcement learning a lot today is Atari games. But I guess who knows what's actually game numbers 42 and 43 or 41. I guess none of the people, or very few of the people who test the algorithm of those games have even themselves played those games. And so when you see an algorithm that has a certain score, how do you know it is actually understood the game or he found a way to hack the system? The only way is to actually to look at the behavior qualitatively and compare it to our understanding of the structure of the task and then do experiments where you change the task in a structured way. For example, you move a certain object to another one, you introduce a distractor, you perturbate the sensors in an organized manner. I think that's also an important dimension.
Shall we switch to the next one? So there were 3 questions on the topic of demonstrations. And so we'll start with, should we use demonstrations to overcome the exploration problem in multitask RL? And how can we preserve generality of the methods?
I would actually argue that in multitask reinforcement learning, exploration is less of a problem than in single task reinforcement learning, because if the tasks share some amount of structure, then you can leverage that in order to explore more effectively. But I do think that in general, using demonstrations to overcome some amount of the exploration problem is a good idea. And in many ways, humans imitate others, and the other people on the panel can talk about this more. Is like we don't always create everything that we do. We see other people doing things, and we recognize when that's something that we should do as well.
Yeah, I guess it depends whether you conceive of the agent you're building as your child or something you want to just leave to it and do its own thing. But like, yeah, we learn most of our kind of detailed knowledge about the world from our supervisors, who are our parents and our peers. And a lot of that stuff took the whole history of human development to work out. And things like language and stuff, you're not going to be learning them from scratch in a single generation. So I think it's fine to try to train your agents the best you can. That would be my perspective.
So I agree that social guidance in general is key. Yet one should not forget that there are many cases where demonstrations are just impossible. So for example, like the most complex sensory motor system children learn is to control their vocal tract to produce sounds. And we cannot observe the movements of the vocal tract of others. We can observe the sounds they produce and get inspired, but then this is emulation, that's not imitation. And so, yeah, sometimes it's impossible, and the same for robots.
Yeah, I'm curious in that kind of example whether you still see a role for demonstrations. So, for example, trying to interpret a demonstration not as a action state kind of trajectory, but something that is higher granularity and where you might still leverage the outcomes of maybe that intermediate goal of producing a specific sound, for example, to leverage a demonstration on that granularity. And another kind of perspective on this, I'm particularly interested in principal solutions that integrate learning from demonstration and reinforcement learning. I think in human learning, we see that integration that happens very naturally, and so approaches in that direction are very exciting to me. Maybe something that you
Yeah, and I think it's fair to kind of question the generality of kind of providing like something like teleoperated demonstrations, because, like you said, there's simply no way to kind of vocalize for an agent. But I also kind of find it hard to draw a hard line between kind of cultural information that's transmitted to you via observation to something like demonstration. They all seem to be kind of on a spectrum of culturally transmitted information that an agent couldn't possibly arrive at on its own. So although kind of things like teleop might be kind of currently a shortcut, I do wonder if there are not like entire regions of kind of skill space that you just could not access if not from someone telling you.
Maybe, oh yeah, go ahead.
One more small thing on this topic is that I guess first I totally agree with like teleoperation, like imitation versus emulation. I think that with like if we can instead get demonstrations just by watching other people in very natural ways or listening to people's voices, then that is in many ways tremendously more appealing. And also I think it's worth mentioning that in first, like the easiest thing to do, of course, is just learning without any supervision, any demonstrations, any rewards. But it's worth mentioning in problems such as robotics, it's actually many times easier to provide a demonstration, even with teleoperation, than to provide a reward function. Because a reward function requires a lot of human expertise, and in many cases, it actually requires trial and error. On this point, on the perspective of the researcher, not on the robot's side of things. So I think that providing kind of weak forms of supervision in terms of like humans doing things and showing that to the robot with their own body is kind of like is a very appealing way to kind of provide some supervision.
I'd like to follow up on, do we have any mechanisms right now, or maybe things we can't do yet, but that we can think of how to incorporate this in reinforcement learning to transfer knowledge across multiple generations? And is that something that we should be doing?
Generations of agents, you mean?
Yeah.
I mean, we're sort of doing that when we develop algorithms, right? And that we develop some algorithm, it doesn't work, then we tweak the algorithm.
Yeah, I guess we're building in, like, we find better algorithms, but would you say we're also passing on domain-specific knowledge?
I mean, when we overfit to benchmarks, absolutely.
Unintentionally. Okay.
Maybe more than we should.
Cool. So unless there are other points about the demonstrations, we'll move on to the next slide. Cool. Oh yeah.
Just one very general point. If you actually care about an application of reinforcement learning, then use whatever data you have. So if that's demonstration, fantastic. If it's the output of some hard-coded initial system, I think in practice people would very rarely start learning from completely random exploration.
Cool. Okay, so we'll now come to a couple of a bit more technical questions. Under the summary of "Tal sounds hard, can we actually make it work?" So the first question here is how to ensure that auxiliary rewards do not compete against maximizing the original reward. And by original reward, I think it is some external task reward.
I was also wondering that.
Yeah, is that even the problem?
I would say it is a problem, and it comes currently down to hyperparameter tuning. If anyone has a different approach, please let me know.
I guess another perspective is you could view like auxiliary rewards and the external reward just as defined in a unified way, and you can actually monitor the kind of interference, because I guess behind this question is the interference that auxiliary rewards might provide to the original rewards. For example, if you have a monolithic neural network that learns a policy that can maximize the auxiliary rewards and the original rewards, it might be possible that the representation that's sculpted by the auxiliary rewards are going to be problematic for the original reward. So I think that here you need a mechanisms for monitoring, a bit like I presented, constantly the evolution of the skills related to the original reward.
I think that this is a challenge in single task reinforcement learning, where you have some reward that you're trying to maximize and you really care about the ability to specialize for that one particular task. And of course, if your goal is to get maximum reward on that one task, then if you add other reward functions or other parts of the objective, you may not do as well asymptotically. I guess this may be just because not that many people are working on multitask RL, but it's not clear to me if this is a problem in multitask RL, or if we even or if auxiliary rewards are kind of the right way to go in terms of multitask RL. I'm not sure, but it's not. I think it's like specifically a question when you're trying to learn narrow skills, and it's unclear to me if it's really a problem when you have more broader skills that you're trying to learn.
So I think possibly the antonym to curiosity in humans is boredom, which seems to be quite an important and not that well understood part of how we so we don't just keep doing something, we get bored of it and then we need to go and do something else. And I wondered if that has like a direct analog in these Turl models, or some kind of vanishing reward for things. So once you've got one thing down, it should stop being exciting to keep doing it. I mean, maybe that's just built directly in, but maybe someone can explain.
Yeah, I think that's actually a really interesting point, and I think it actually is more about how we're evaluating our models versus actually how the algorithms themselves are doing. And like if you're evaluating based on asymptotic performance on one task, like of course, like it's okay to like boredom doesn't matter. Like you should just keep on doing that thing over and over again repeatedly. But if we instead are evaluating based on something more like generality and the ability to kind of continuously increase complexity of the things that we're learning, then things like boredom matter a lot more. And I think that things like auxiliary rewards would be potentially more helpful.
I feel like in some ways this question is just kind of restating the entire problem itself, which is it assumes that there is an original reward. And if anyone knows the original reward for task-agnostic learning, like please come up and say it. It seems like defining a general original reward for kind of a lifelong agent is very much like the open problem. And something that might be an auxiliary reward to a single task could very well be the main reward to a different task. So I'm not really clear on yeah, it seems like in a multitask setting, you should care about the kind of the enumeration of all of your hard evaluation tasks.
Perhaps a follow-up question here is, if I don't know the goal space for tasks that I want to evaluate my agent on, and instead the agent learns its own goal space in a task-agnostic way, are there any good ways of using the very same agent to then evaluate it on those downstream tasks? Because it's a problem, like if let's say I don't have a goal-conditioned agent and I have it just explore the world, how do I actually evaluate that at the end of the day? Or should we not be working on those models?
I think that we can evaluate on downstream task performance. Like if it's exploring, you can evaluate on its ability to transfer and adapt to new settings, just like some of the work that we've seen in this workshop. Yeah, on adaptation, exploration, etc.
I think it relates actually to a question Chelsea mentioned in her talk, and more general question, which is how in the end downstream tasks are specified by real users, which means users which are not engineers in the lab, but like non-expert users outside. And so one approach like is to show images, like Chelsea showed. Another approach, which I think is very fundamental and we should develop much more in this area, is natural language. And then it relates to an open area of research, which is how an agent can learn the mapping between natural language instructions given by a naive user to the internal representation of goals that it has learned. So maybe those internal representations, they won't be accessible directly and understandable by the human user, but through the loop of interaction using natural language, then in the end, the end user can ask to the curiosity-driven thing that has learned a number of things. Then in the end, it can ask, okay, can you show me that, but in natural language?
Sort of a nice property of natural language is that it's symbolic and it is inherently abstract over what could be considered like a large goal space of images. It's something that necessarily collapses to a much lower dimensionality. So it kind of has abstraction built into it. And then even more so might be something like learning binary human preferences or learning an agent that optimizes for like kind of a single bit of information. It seems like if you want truly task agnostic, you kind of need this level of abstraction in the goal space or the task specification.
It seems like this is implying that the agent may be using a different goal space for exploration than, let's say, a natural language description for evaluation. Is that something that we agree on? Yeah? Everyone agrees on that?
That is possible, yes.
Okay, interesting. All right, let's move to the next question. If we build a truly task-agnostic method, how do we ensure that the resulting models or policies are actually useful? What stops them from learning useless skills or information? All right, we can move on to the next question.
Yeah. I guess this is something I was kind of trying to address in the beginning of my talk. I was trying to be a little controversial and kind of claim that when people talk about task-agnostic agents, that really they do have some distribution over tasks in their mind that they're really trying to actually achieve. And so if it's not consciously built in, then I think there are still underlying assumptions, and in the end there is task structure in. Now, that built-in structure may or may not reflect what the experimenter is actually trying to achieve, in which case they would probably claim the experiment failed. But I don't know if there's any more kind of systematic insights into how to avoid that.
Maybe a complementary comment is that this question assumes that there is a notion of usefulness. And in a way, this is formulated from an engineering perspective, not so much from a scientific perspective. So in a sense, like maybe actually we should take a little bit of a step back by looking at studying those algorithms and studying them a bit like a physicist or a chemist would study a chemical system or a physical system. When he's studying a chemical system or a physical system, the physicist is not trying to answer the question, is it useful or not useful? He's trying to understand how it is working. And so in our case, I think it means trying to understand a little bit better how a family of algorithms, what are the properties of a family of algorithms in a certain distribution of environment, how these properties are changing into another distribution of environment. And it's not about like being better or worse than another algorithm. It's really about understanding this as a physical system.
One other thing to potentially think about here is that in my mind, well, I think that we all potentially have our own definition of task agnostic, but I think that in my mind it's in many ways thinking about an agent that can do many different things in a single environment. And so one thing that you can learn from that environment is about the environment. You're learning about many different tasks, but in a single environment. And so even if you don't learn something that has like kind of this right structural priors about the types of tasks you'll see at test time, at least you'll be learning something about the environment, and you can use that knowledge of the environment to do better than if you were to learn completely from scratch.
Yeah, I'd echo that. I've been understanding task-agnostic reinforcement learning as about getting general flexibility and competence in an environment, such that I could then give you any goal and you can learn, and so it should be something that you're basically becoming equipped for the future where you don't have an idea about what will happen next. So it's that flexibility I think is good, and I don't see the need to analyze it beyond that really.
Cool. I think Chelsea's already answered the fourth question on the slide earlier on. But we still have one question, which is a continuous skill space seems to be good for related skills. However, how can we learn new distinct skills while preserving the continuous skill space for previous skills? Maybe on a bit more general level, do you think, what are the trade-offs between continuous task or goal spaces versus discrete spaces. So we've seen a lot of methods today with variational autoencoders that learn continuous spaces, and on the other hand, there is, let's say, diversity is all you need, where you have some categorical variable.
I think that this is probably like a general question for all of representation learning, though. It seems like, in general, you could imagine there's like an entire class of things that you might want to represent that have some inherently discrete structure, and some entirely separate set of things that might have this like nice like continuous and ability to interpolate structure. I could imagine, I think the second part is like adding new distinct skills, like presumably you could just kind of add like append a skill to a set of skills, and kind of hope that the rest of your architecture works. It's not, at least I've not seen work that allows this to happen. Oh, no, sorry. Yeah, it seems like in a lot of cases where you might want to just kind of like add a new distinct skill to a set of discrete tasks, you very much need to like learn a new mapping to this kind of new ID. And it's not clear to me exactly how a discrete versus a continuous representation makes it easier to add new skills. Does anyone have any ideas?
I don't have an idea on the question that you were posing, but some thoughts on this is that I don't, I guess, well, in general, I think that like the more tasks, the better. And so in that regard, sometimes, in some ways, continuous seems more appealing, although if you have a combinatorial number of discrete skills, that also seems, that seems good enough. I also don't think that there needs to be a huge distinction here. I think it is kind of really about the representation learning. And a VAE can still represent discrete structure. Like your neural network can transform that continuous space into something that is more discrete. And so while the representation may be continuous or discrete, what it is representing might be something different than that.
So with that, let's move to the last slide. We have a few minutes left, and we've already touched upon representation learning. So here are a few questions about what a good task-agnostic representation actually is. The first one I think we've covered with the last question. Another one is how to represent global knowledge about the environment. And two suggestions here that were made are either universal value functions or maybe dynamics models.
I mean, this is basically like model-free versus model-based. I think it's still an open debate, and I think right now there are settings where one works better than the other. But in different contexts, I think that, yeah, I think it's in many ways an open question still.
I'm just kind of team model-based when it comes to thinking about cognition, but I think it's hard to underestimate how having a model allows you to think creatively about the world and its alternatives, and be imaginative and come up with new solutions and things if you have this model that you can play with and tinker with. And I don't see how that comes out of the model-free perspective, but maybe someone can correct me.
Just following up on that, I'm curious about your what you think of a talk that Matt Botti gave at the Spiral workshop. So he was showing a lot of evidence of how model-based like behavior actually emerges from simple model-free approaches. So for example, model-free reinforcement learning with LSTMs and a large amount of data learns something that looks like planning on complex tasks, for example. So a key question to me is, are we seeing planning and explaining post-hoc as in, yeah, there must be a model somewhere in there, or could it be possible that it's just emerging from relatively simple algorithms in a very complex environment and lots of data?
I mean, yeah, it could be. I think that the goal test is to have a completely new goal that's never been faced before, but that can be solved with a model if you've learned it. So I would want to see evidence that people flounder when they're doing something that they should be able to do if they had a model, but wouldn't be able to do if they had if the model-free values are all entrained to a past goal, which is no longer their goal. And I'm not sure where the evidence is in a lot of cases, but I'm sure it's also a mix. And wherever we can be model-free, we're going to be model-free. But wherever we need to be flexible and we can't predict what goals we're going to have in the future, I think we're going to need a model. And when it comes to interacting with the world for the whole of your lifespan, it seems like you're better off to try and build a model of it than to try and learn model-free behaviors for every possible situation.
I think this connects well to the last question for today, which is, can representations be learned from limited data that are meaningful for exploring unseen state regions?
Maybe a comment about that. So several of those questions relate actually to learning generative models from which one can sample goals or tasks or auxiliary tasks. And I think there is a major challenge for the community in this domain, in the sense that for especially intrinsically motivated exploring agents, the idea is that they need to explore and discover things they've not seen yet. And we've seen also in different talks that one way to do that is by generating some tasks or some goals that will lead them in those places. So it means that they should be able to imagine some goals that they have never seen. And so it means we need to learn generative models that extrapolate. And I think that's a key challenge for the future, and that goes at odds with most of the existing methods for learning generative models, because right now the way they are built is that they are built to match the distribution of observations they've seen. But what we need for exploring the world is to be able to imagine things outside this distribution, and that still makes sense. They don't need to make sense all the time, but sufficiently often that when we set that goal, sometimes we make interesting discoveries.
Similar to, I think, what you're saying is that I think that in the general case, I would argue that the answer to this question is no, because it breaks kind of the standard paradigm of machine learning, which is that your training and test distribution should be the same. And if your test distribution is different, then there's no reason to expect it to generalize. If you're using kind of black box machine learning based approaches. If you incorporate some sort of structure into that process in some way or another, then in principle you should, maybe there are ways to extrapolate it. And of course humans are an example are basically a proof of existence that we can extrapolate in situations and figure out how to explore in situations by making analogies. But machine learning on its own isn't going to get us there, in my opinion.
I fully agree, and just to add on to this, some of the experiments that I showed in my talk with the first model, so the one that encapsulated dynamics in a GP model, that was able to extrapolate two areas of the space that it had not seen during training, and the way it achieved it is by the choice of kernels. So it's something about the structure of the task that we know and that can be built into the model to allow extrapolation. Similarly, there's a small amount of very exciting work where people look at, for example, incorporating existing off-the-shelf components like planners or like access to a database into a model that is otherwise learned end-to-end. And I think those are really exciting directions for understanding how maybe we could dramatically move beyond the space within which an agent has specifically been trained.
With that, I would like to thank our wonderful panelists